Okay, so maybe we can start. And for today, for the first talk, it's a pleasure to have Xavier Bekaert from Tours that is talking about BMS particles. So the format is the same, so 1 hour slot with a lot of questions.
Okay. Thank you very much. And indeed, thank you to the organizers for the possibility to come and present this work. So I would like to talk about unitary reducible representations of the BMS group and of course thought as particles in the presence of BMS symmetry. This comes from a joint work with Laura and Yannick. And the big motivation is of course, the dream that many people have to try to build a BMS invariant S matrix. And the motivation is that indeed, in the presence of gravity, one would expect BMS to play a role, and in particular for scattering processes. Okay, so that's a big challenge. So maybe one way, a humble way to try to approach this is to look for a streamlined approach. And one simple way would be really to simply take the Weinberg's book and try to replace everywhere blindly Poincaré par BMS, with BMS and see how far you can go. Well, that's not what we will do. But as a first step, you can at least open the chapter 2 and try to follow the group theory as a useful guideline. And so basically, we would like to push the idea that to build the Hilbert space of asymptotic states in this context, you would like to think as a suitable Fock space, just tensor products of one particle state that span a unitary reducible representation of the BMS group. So this will be our working definition for a BMS particle. And in practice, a lot of works have been done. Fortunately for us, on representations of BMS, but we would like to revisit them with modern insights in mind. Okay, so indeed, many works have been done. So what are the main milestones on the unitary reducible representation theory for BMS? So first of all, we can start with what's simplest, so Poincaré, so the well-known work of Wigner. As we know, Poincaré has the structure of a semi-direct product between Lorentz and translations. And the useful property is that this one is semi-simple, so we know its representations, and this one is abelian, so we can make use of this to build the representation. And this is indeed how Wigner introduced his method of induced representations. And that was generalized later by Mackie to a much more general case where, for instance, you can have a semi-simple group acting on an abelian normal subgroup. And basically, this is the setting in which we are, because BMS is Lorentz acting basically on super translations. And so it has indeed this kind of structure. Of course, a big challenge is that, well, here it's finite dimensional, and here it's infinite dimensional, so of course many tricky things can happen. So one of the first that worked on that was Cantoni, and then there was really a long series of papers by McCarthy in the 70s. And there are indeed some subtleties, since in infinite dimensional, it's a bit tricky. You should really be careful about the topology that you choose on the space of super translations and so on. And in fact, there was really an important paper by Girardello and Paravecini that clarified the correct choice of topology. I will not enter into details, but at least it's important. And then also there was a proof of exhaustivity, at least for Hilbert topology, maybe not for the correct topology, by the way, by PR. And finally, there are also the realization that may contact more with what we would do as physicists in terms of field theories and so on. And so there were important works by Sachs, Ashtekar, Longhi Materassi, and other people. Okay, so you can do the same for BMS in 3 dimensions. It's of course interesting, and But I will not do that. So it's a pity. So here we have varnish and black, and here it is a melas. We'll continue somewhere, yeah. No. No. As far as I know, the answer is no. No. But I don't know. I mean, who knows? But no. As far as I know, nobody looked at that. It would be interesting, of course, but so the answer is no. Yes.
You can have super translations, right? But can you include it like in the same way, or?
So, indeed, even if you would put super rotations here, of course, then you would still have this kind of structure. So morally, yes, and by the way, in 3D, that's what they did. Huh? But we did not do, and for us, as I will argue, it's a big simplification that this is finite dimensional. Because of that, the orbits, so if you want the BMS mass shell, are finite dimensional. And so in this sense, the representations are still friendly in this respect. I mean, so I will not discuss about it at all, but of course it would be of interest. So here is the plan of the talk. So there will be an introduction where I define things, etc. And also where I will introduce the crucial ingredient, that is the composition of supermomenta into hard piece and soft piece. That is really instrumental to make contact with the modern discussion. And then I will move really to the classification of BMS. And finally, yes, I will conclude. So, super translations and super momenta. So I know they are experts, so some things maybe I will go a bit faster, but let's try to be self-contained nevertheless. So to discuss the BMS group, of course, the natural locus is null infinity. So this cone is a bundle of null rays. So more precisely, it's a R principal bundle. And the sections of this, the sections like this, of this ray bundle are called cuts. I introduce them because the wave functions, the analog of wave function in position space, for BMS representation, they are wave functions on the space of cut. That's why I introduced this notion. So basically, in terms of conformal, of Carolian geometry, they can be thought as simultaneity slices on scry, with respect to retarded time. And each cut is preserved by a Lorentz subgroup of the BMS group, which is acting on this sphere. So these cuts are homeomorphic to spheres, diffeomorphic to spheres, and they act as conformal transformations on the conformal sphere, basically. Okay, so many objects indeed have a natural transformation in terms of conformal geometry, which is the language I will use. And as I will argue, yes, that's what I mentioned, the wave functions of BMS particles, the analog of the position representation, you can think about them like wave functions on this space of cuts, which is this homogeneous space. Okay, so I will need the notion of conformal density. So conformal density of weight W, I basically mean a scalar field on the sphere, which transforms with this weight with respect to a Weyl transformation. So quite often I will use the standard abuse of notation. I take one representative, and just to be clear, I will always work in the flat metric representative of the conformal class, because formulas get much simpler. So that's what I will do. So in practice, really, we will mostly need the Lorentz group. So basically, Möbius transformations. If I think about the sphere in stereographic coordinates. And so they transform as follows, the weight W densities. And one important assumption related to your question, I will always assume that these densities are smooth and globally defined on the whole sphere. And in particular, this implies an important property, which is a pity that there is this. It will be quite often, I'm afraid. I can move this. It just. Are you sure I can? Anyway, so indeed, I can write it on the blackboard. So this is an inversion, okay, of the celestial sphere, and where you take the origin, you send it. Okay, thank you very much. Yeah, this will save some time. So you can take an inversion, so where you send the origin to the point at infinity, and since it has to be global everywhere, you can obtain by this kind of weight, that you take into account the weight, that actually the wave function, the conformal density, I mean simply, when z goes to infinity, it should scale like this. So in particular, when W is negative, which will be the case for supermomenta, this means that things decrease, must fall off sufficiently fast at infinity. But now we lost the the connection here. You can try, but but even here, you again. You should just click maybe on the okay, no, indeed, yeah. Thank you very much. That was simple, but too hard for me. Okay, so yeah, super translation. So they are vertical automorphism of the fiber bundle, and in practice, so we just shift the retarded time by a function on the celestial sphere, which is, if you look at the weight, indeed it has conformal weight 1. So that's what super translations are from this point of view. And the BMS groups, therefore, it's just the semi-direct group where you act by conformal transformations on these weight 1 conformal densities. Okay, so as we know, translations are canonical inside super translations, and so in more fancy terms, so there is a canonical Lorentz invariant linear injection like this of the translations inside the super translations, which is given explicitly by this. Very well. Okay, so the idea is that we would like to build wave functions. So one thing that looks very natural, and that is natural from the point of view of the method of induced representation, is to consider, I mean, since you have an abelian normal subgroup, you would like to diagonalize it. And so that's what we do. So we have the usual momentum basis, and we would like to generalize it to the super momentum basis of, yes. We would like to generalize to the super momentum basis of eigenvectors of super translation generators, okay? So as a side remark, this is important again for, it's technical, but important to keep in mind. So when you send Lie algebra, you take its dual, because you send it, you see here to eigenvalue, so clearly we are in the dual, but since the space of super translations is infinite dimensional, we should really take here the dual in a well-defined sense, and in practice here we should take the continuous dual. So we have to be careful about that, and it's really unavoidable. It's not like being fancy, it's mandatory. Okay, so super momentum, in a naive way, if it would be simple, it would just be a conformal density smooth of weight minus 3 in such a way that it's the dual, so when you integrate, it has the correct weight. But actually, you have to go beyond in general, and this was lacking at the beginning in the analysis of McCarthy and corrected by Girardello and Paravicini, that you really have to consider distributions on the space of, yeah, clearly here it's super translations. Sorry for the typo. Okay, so in this basis, the nice thing is that super translations acts very nice, simply, just by phase shifts. And yeah, as I said, we will see that wave functions, very naturally, they will be wave functions of super momenta, but clearly by formal Fourier transform, you can have wave functions which are wave function on the space of cuts, as I said. Huh? Okay, so we have the injection of translations inside super translations, but the dual of this is the following fact, that super momenta, they project. So there is a canonical Lorentz invariant surjection, which is linear surjection of super momenta onto momenta. And again, yeah. Yeah. No, I just mean that if you take an off-shell here, in general, this off-shell, I just mean I'm not necessarily on a given orbit of the Lorentz group. That's what I mean. A BMS shell, it will be a Lorentz orbit. And in that sense, if I take any guy here, it will be any guy here. And so they are off-shell in this sense. But later on, I will consider on-shell to be reducible, on-shell wave functions in supermomentum space. But what we don't know is how they are described in terms of on-shell in the usual sense. We don't know the field equations that make in BMS space, if you want. Yeah, that's what I meant. Okay, so we have this injection, surjection, sorry. And basically just that if you take a super translation, which is a translation, then you expect, of course, to just reduce your problem to momentum contracted with a translation. And that's what you have. Huh? So when you make usual translation, they just transform, supermomentum states transform in the usual way. Voilà. Okay, so since we have this surjection, then you can consider its kernel. And this is what we will call a soft supermomenta. So these are supermomenta whose associated momentum is 0. So supermomenta annihilate translations and vice versa. And yes. Okay. Yeah, please. Okay. Just going too fast, okay. Yeah, sorry, there is a lot of text in the slides, maybe. It's true that, but okay, so let's nevertheless proceed. Okay, so now comes a question, which is how to characterize this soft supermomentum concretely. And there is a way, so there are some general results of Gelfand on the representations of the Lorentz group. And you can dig from these results that soft supermomenta, so their projection, they have 0 momentum, they can be written in this way. So in other words, they are in the image of the Laplacian square, if you want. So there is a notion, a conformally invariant notion of the Panet's operator. It's a conformal invariant. And it acts indeed on super translation, it has the correct weight, etc., to be conformally invariant. And so there is the notion of the square of the Laplacian, and that's what you have. Okay, so soft supermomenta, they necessarily take this form. They are in the image of the Panet's operator. And also you have the following, that you can ask yourself, what is the kernel of this Panet's operator? And they are basically the translations, in fact. Yeah. Yeah, exactly. Yes. So Panet's operator exists in any dimension, but in this simpler setting, it's just this guy. So it's a Oh, but then you need like curvature terms and stuff like that. So they belong to the JGMS list of operators. So yeah, it's all under control. But here it's really friendly. It's just a fancy name for this operator at the end of the day. But it has a conformally invariant meaning. That's the important. Yeah. And by the way, this I will not discuss, but many of these things, they can be, in fact, generalized to BMS in any dimension bigger than 4 as well. Yeah. Many things are smooth. Not everything, but there are things I have no idea, but most things can be done. At least in even dimension. Okay, so yeah, let's. Yeah, of course, yeah. I mean, it has conformal weight 1. Does this sense?
Yeah, I'm just saying that there's a conformal multiplet for the operator associated to super translations, and this n is so that's
So I mean, in this context, since it's for supermomenta, I would not call it super translation, but I mean, it has the correct weight to be.
Yeah, it's the sort of the symplectic partner. Conformal multiplet to the super translation multiplet.
Yeah, we will. I mean, in the paper, Laura, where we made contact with the.
So this is the eigenvalue of. Yeah, I understand. It's from the memory diamond. Yeah.
I'm also a bit confused by the statement about conformal invariance. So in the usual case with the sphere topology, then this type of operators. In the usual case of round sphere topology, usually it's convenient to restrict attention to those conformal transformations that preserve round spheres, and then these operators are conformally invariant. But if you are using arbitrary conformal transformations, often they're not. So when you say these operators are conformally invariant, do you have in mind the restricted class of like BMS type conformal transformations, or you're really saying that for arbitrary conformal transformations, you don't need anything like a Garroch tensor?
Smooth.
Sorry?
Smooth.
No.
So you never need a Garroch tensor in constructing a conformal invariant?
Well, indeed. So, I mean, the right terminology shows that they are Mobius invariants. They are SL2C
invariants. Okay.
This is what we mean here always.
No,
You're
that's
right.
true.
They are not conformally invariant. I mean, there is a difference between this operator higher dimension. That's
no,
what we
sorry.
mean.
Then indeed, I was confused by your question, but yes. Yeah, sorry. Indeed, in higher dimension, they are really Weil invariant. Here, they are only SL2C invariant. Yes, I'm sorry about this point. Yeah, sure. Yeah, that's important, but yeah, sorry. Okay, so it's important to that's what we want to stress. So there is no Lorentz invariant linear injection of momenta into supermomenta. But that's why there is something that exists, and indeed there is a decomposition. The price to pay, if you want, is that you have to relax linearity. So it will not be a linear map. But if you relax this, you can definitely define, so for any supermomentum, it's equivalent to a pair of a momentum and what we call a soft charge, which is indeed in this equivalence class and related to your question. And that's the decomposition where I will tell you in one slide or two what is P. Yes, so this is the terminology I just said. And the hard supermomentum will be the piece, it will be the case when the soft part is absent. So this is a hard supermomentum, which I have to tell you what it is, and here it is, concretely. So basically, it's if you remove all the factors and complications, it's just you take the momentum, here it should be small p, sorry. So momentum contracted with the Q, I told you, for the translations, the injection of the translation. So you contract, this is of weight 1, because this is of weight 1. So to be of weight -3, you just take the power minus 3. So this is in the massive case, and in the massless case, this would not be perfectly okay because it has, I mean, it gets infinity. Huh? It has a 0 inside here. So it's not well defined everywhere. You have to regularize, and one way to regularize is just to take this Dirac delta. So that's why you see that necessarily you have to go beyond Hilbert topology. You really have to look at distributions. Otherwise, you don't have massless particles. Yeah? Mm-hmm. Yes, yes, yes.
Physical degrees of freedom. Therefore, I'm asking, have you done this? What's the action for these different particles?
So at the end, I will comment on but I can already answer partly. So in general, the orbits will be bigger than in the Poincaré case. So in that sense, I would say they have much more degrees of freedom.
But have you counted that?
I mean, it's the dimension of the orbit. So yeah, it depends how you define.
In 3 dimensions, at least for the massive case, the physical degrees of freedom coincides with one of Poincaré. Therefore, in a sense, from this point of view, it seems like a decoration.
But
like,
if you want,
we do in a gauge theory, we have the 2 degrees of freedom, but it's not nice to look at it. And we introduce gauge degrees of freedom in a way that we can see easily the properties.
I mean, what I try to say is that these extra, so the orbit will be bigger, and these extra directions, if you want, with respect to the Poincaré orbit, in practice, from the Poincaré point of view, you interpret them as spinning degrees of freedom, and they are in general infinitely many. So that's my answer.
But there are infinitely many gauge transformations also.
Sorry?
There are infinity many gauge transformations, therefore you should convert this in second class and
No, sure, but this is all good, but this is Hamiltonian formulation. It's perfect.
I'm thinking also in
Sure, but that's what I mean. But here it's unitary reducible. I mean, it's a bit different language. That's what I mean.
Maybe.
So we can discuss if you want, yeah. Okay, so yeah, so there is indeed a one-to-one correspondence between momenta and hard supermomenta in this sense. Notice that they are indeed nonlinear. Huh? As you can see, it's power minus 3. And that's it. Let's proceed a little bit. So summary, yeah, we have a decomposition. And something important is that indeed it's not stable under addition, since it's not linear. And indeed, in practice, physically, you can think about it like this, which is a well-known fact, that if you take not in this language, but so if you take a sum of momenta that are conserved, their corresponding sum of hard supermomenta will not be equal to 0. There will necessarily be a non-zero soft part in it. Yes. Yeah. Yeah, sure.
Genuinely the usual.
Yeah.
I think this is.
Maybe this is also related to your question. Yeah. If I just take hard supermomenta, so the representation with hard supermomenta, they identify with the Poincaré particles. So maybe this is what you were seeing, but we have more. That's what I want to say. We have more, but it will become hopefully more clear if I proceed. This we can discuss, but yeah, I cannot comment.
Yes, but for the numerical transform, I don't see immediately how you construct the action.
Maybe Xavier
Yeah, I
will show
would
wave
say-
functions. Maybe you will see
Yeah,
explicit
hopefully
wave
I will
functions.
reach there. I'm not so sure, but hopefully. So the big question is, like in the title, what are BMS particles? And well, there are various proposals, like this Fadeev-Kulish states and so on, the cloud of soft particles. That's all good, but so here, the idea is to take a very agnostic answer and to think about them like unitary reducible of the BMS group. And related to all this discussion, in this group theoretical point of view, then you should also ask yourself, but yeah, okay, fine, but what are then the usual Poincaré particles? And the answer to this is in terms of the, well, technical term, the branching rules of the BMS group when you restrict the BMS group to the Poincaré subgroup. So this is how you will recover the usual Poincaré particles. Okay, so and maybe I will not go a bit faster on this. Well, as we all know, to define anyway a quantum field theory as a vacuum state, by definition you have a Poincaré group, and this is how you define your Poincaré vacuum, right? But here in BMS, clearly we have infinitely many Poincaré subgroups of BMS groups, and there are as many as gravity vacua, and in terms of QFT, this is precisely for each of them, you would like to define the Poincaré vacuum for each of them. So, okay. Sorry? Well, this is second order question. I mean, you may consider this subclass, but yeah.
Cannot be separable. In fact, the big, the ghost of Banco in all this story is that, I don't know if this is on, but anyway, is that has all the characteristics of a spontaneously broken group. When you have a spontaneously broken group, you do not look for unitary representations. In particular, you do not look for eigenstates of P. Think about the simplest case, which is a scalar, a massless scalar in more than 2 dimensions. It is invariant under translations. Well, you know that the vacuum is not an eigenstate of the momentum, right? It's, in fact, you have infinitely many, uncountable number of states that are eigenstates, if anything, of 5. Right?
No, indeed.
For each of them, you construct a representation of the unbroken group. The S matrix actually is not invariant. Right?
Yeah, exactly.
It's covariant, it transforms from one vacuum to the other. And here you have a very similar situation. I mean, if you think about memories, right, they cannot be changed by operators that are locally retarded time. So they really look like I guess states of the memory of P, right, looks very much like
Yeah. But then my next question is if there are any super selections or...
Well, by definition, when you have a broken symmetry,
Yeah.
and you act with local operators, and you construct S matrices by, say, an LSC of local operators, you are always in a super selection sector. You never go from a value, a VEV.
Yeah, so each of these vacua is a super defines a super selection. That was my question.
Vacua are not even observed. You cannot change them by any local operation. Any local operation in the development time. So all of this smells of province. And then you know that you don't want to look at unitary representations of province. That's the wrong approach.
You're not expecting, just to make sure I understood the reason. So you're saying you should look to BMS representations, and you should not expect that if you branch them to Poincaré under the Poincaré group, that you should get a separable Hilbert space or good.
Branching is separable, right? But think about again U1 translations. Then branching is separable, but not in the big Hilbert space is non-separable.
Yeah. Each of the sub-representation is separable.
Each of one, yeah, but you don't. The S matrix may be decomposed in some super selection sector. So when you act with BMS, go to another S matrix that is equivalent And instead it's not a unitary transformation separate from unit states.
Yeah.
Associated with super selection set.
Yeah. Thanks.
Okay, but so to be clear, what we will obtain, which I presume we will never reach, but so for one unitary reducible representation, the Hilbert space, so of one particle, is definitely separable. What is becoming tricky is, of course, once you build for all possible particles, then it would be very natural to expect it to be indeed non-separable, but it's still a possibility that maybe you can restrict partly, but this I have nothing concrete to say. Okay, so I think I propose to go to the juice, otherwise. Okay, so just let us start smoothly by very quickly reminding, in order to compare and give the logic, how it goes for Poincaré. Okay, so we use the fact that it's indeed a Lorentz group acting on a abelian normal subgroup. So the idea is you first consider the unitary reducible representations of the abelian subalgebra in this case. They are labeled by real eigenvalues, because since it's unitary and irreducible by sure lemma. And in practice, so you characterize states by momenta, at least temporarily, then you will consider orbits and play in the usual way. So indeed, you look at orbit and stabilizer. So the orbit, we think about it like the mass shell, and the stabilizer, we call it the little group. And then, what do? You have to induce the representation from picking, unitary reducible representation of the little group. And then you induce and you reconstruct your whole representation of the Poincaré group. And the choice of representation of the little group gives you the spinning degrees of freedom, or Okay, so clearly the wave function has support on the orbit, which is three-dimensional in this case, and will be, in the BMS case, not much bigger. It will be finite dimensional. And yes, okay, good. So we do the usual classification. We get the usual orbits. And the orbits are cosets like this, which can be, by the way, also seen as a, if you go now in position space, as the boundary, where you put the boundary data. Okay, so this is all fine, but maybe let us focus on the interesting case of BMS. So, okay, now we have an infinite dimensional abelian normal subgroup, but still we proceed in the same way. We look at the eigenvalues of the generators, and this gives the supermomenta. We look at the orbits and stabilizers of supermomenta. You choose one, and you look at orbits and stabilizer. And you have to pick a unitary reducible representation of the BMS little group, so the stabilizer of a supermomentum, which, by the way, is a subgroup of the Poincaré little group. I mean, it could be equal. They could identify, but it's for sure not bigger. Okay, and the good news is that because of the method of induced representation, the wave function is a wave function that has support on one orbit, if the representation is reducible, and this one, it's finite dimensional since you act on the supermomentum with the Lorentz group, which is finite dimensional. Okay, and these wave functions, they take values in the representation of the BMS little group. So basically, that's all, except that you have to do it and classify it, and that's what McCarthy did for us. I will not go into many details, but that's the philosophy. Okay, so as I insisted, all orbits are finite dimensional. Another remark is the hard and soft distinction. It was Lorentz invariant, so clearly it also goes for the representations. And so hard, soft representation, they are respectively representation where the momentum are hard and soft, respectively. So, as was already mentioned by Yannick, when you have hard momentum and the corresponding orbit, in practice, the BMS and Poincaré little group, they coincide, and therefore, the corresponding orbit also coincide. So in practice, this means also that the wave functions coincide. So the hard representations of BMS group, they are just the good old Poincaré representations seen in terms of boundary data, basically. Okay, so much more exotic already are the soft representations, so where the momentum is soft, because there, from the Poincaré point of view, they have zero momentum. So they correspond to this weird representation in the classification of Wigner, where the zero momentum representations, which are not interesting physically usually, since they are representations actually of Lorentz and not really of Poincaré. But here it's quite different. Here they are really physically important and distinct. And finally, there is the generic case where both of them are zero, hard and soft part. And in that case, the little group is just the intersection of the corresponding stabilizer. Okay, so this I mentioned. So really we have an identification like this. That's the nice case. Yeah, please. Yeah, that's why Yannick mentioned. So this we agree. But then there are many more. That's all we mean. Sure. But the burden is on your shoulder. That they are here. I mean, I agree. It would be interesting, but yeah. So the zero momentum representations of Poincaré. So in practice, they are just representation of Lorentz group. So usually that's why we never look at them physically, because they are a bit silly. But if you do the same logic for the BMS now, since translations act trivially, in practice, the soft representation of the BMS group, they are in practice really faithful representation of this quotient group. That was called Comar group by McCarthy. Okay, this we have not studied them in detail. So this is worth investigating exhaustively. We really looked at the generic representation, so where hard and soft part are non-zero. Okay, and just to give you a flavor, and then I will conclude. So here are some tables with the list of the size of the shell, the BMS orbit. These are just the BMS orbit, that's the Lorentz orbit of the supermomentum. That's what I mean by BMS shell. So let's take the totally generic case where supermomentum, which has trivial stabilizer. So trivial BMS little group. In that case, well, since Lorentz group is 6-dimensional, the orbit will be 6-dimensional. And if you project, you have three possibilities: massive, massless, and tachyonic, with the corresponding little groups. And always, for Poincaré, the dimension is 3. And the opposite extreme, then we have the hard representations, where the BMS little group, they coincide with their Poincaré ones, and the BMS shells also coincide with the usual ones. Okay, so these are the extreme cases. Now let's look, just to give you a flavor, for instance, what happens for massive momentum. So supermomenta whose projection is a massive momentum. So you can have a trivial BMS little group, in which case, again, this is what I discussed before, you have, the orbit is 6-dimensional, but you can also have a BMS little group, which is SO2. And in that case, if you make the counting, so this is 1-dimensional, 6 minus 1, indeed 5. You have 5-dimensional BMS shell, which are indeed 2 dimensions more than the physical, the usual mass shell of Poincaré. And this will correspond to 2 directions where you could have extra physical degrees of freedom in this sense. And finally, you have the hard ones where they coincide. And okay, what we did also is to look at the massless case, and you can see you have various little groups, SO2, but you could also have R square, and ISO2, so which does not coincide with the hard. There are some, that's a bit weird, but there are some supermomenta which project to massless momentum, which have BMS little group, which is ISO2, like for the Poincaré little group of massless momentum, but nevertheless, these supermomenta are not hard. Okay, they contain a soft piece. So this is a bit exotic. And finally, there is the hard supermomenta, and again, this just coincide. Are there some questions? Because actually, since I rushed at some point, I will go to the conclusion. It's not done, but I go to the conclusion, basically. Mostly go to the conclusion after. Yeah. Yeah.
Technical question. Since you're working with a non-separable Hilbert space, do all the standard procedures of constructing representations, induced representations, etc., work? Because now you cannot use finite induction, right? I mean, countable induction.
No. But so yeah, indeed. Let us insist on this. So these representations, they form a separable Hilbert space for one unitary reducible representation, and it is nothing deep. It's just that you have a BMS shell which is finite dimensional. So you just do usual. I mean, it's measurable. So there is no problem. You take square integrable functions on a finite dimensional space, so there is no issue of separability. Do you see what I mean? If you want, but it's just group theory. I mean, you do square integrable functions on this, let's say, pick your favorite one, the 5-dimensional one. No. I mean, come on, it's like the... I mean, it's like on the circle. I mean,
maybe just a comment. I mean, so if you as BMS particles, as wave functions for BMS particles, they are separable Hilbert space. Now, when you're trying to think of them as Poincaré particles, and you branch this into usual Poincaré particles, then they look like a non-separable numbers of usual Poincaré particles. But as BMS particles, the Hilbert space themselves, they are separable about this. So,
no, this is 200% solid. Yeah. For one BMS particle, it's separable, no problem. Because it depends on the choice of the... I mean, we can discuss after that. But this is for sure. Where things become tricky is when you would like to consider not a finite collection or countable collection of such BMS particles. Then you may need indeed a non-separable space. But for a countable collection of possible BMS particle species, it's separable.
Yeah,
so we can discuss, but this is 100% rigorous mathematics. Huh? There is no issue to there is no debate about this.
You see, that's, I mean, you have the same phenomenon in broken symmetries. If you take a group G and you look at irreducibles, well, those are always either finite or separable, right, Hilbert spaces. On the other hand, if the group G is broken to a subgroup H, and then you want to study, I don't know, the S-matrix scattering, etc., then you have some pointer, right, like the VEV of the Higgs, and that gives you a non-separable Hilbert space because you have a continuum of, say, eigenstates of an operator, and any two of them are orthogonal, are strictly orthogonal. So, again, my question is, are those the correct representations? Because are not irreducible representations of a broken group are not the right tools to study a broken group.
No, seriously. If original representation of your group G is separable, whatever you branch it to, it will remain separable.
Yes, but then the big representation does not act on a separable Hilbert space. So that's the point, right? If you branch.
It is already, if initially it is separable, what do you mean?
That's a red herring. Come on, think about a U1, a massless scalar, in 3 dimensions, okay? A massless scalar in 3 dimensions. That's not too complicated, right? Well, I mean, if you look at the representations of translations, well, definitely they are super separable, right? I mean, it's a one-dimensional Hilbert space. On the other hand, if you want to think about the field theory of that space, it decomposes into a sum of separable Hilbert spaces, But the sum is non-separable because it's labeled by a continuum
But it
of
depends on
orthogonal
the basis
states.
that you choose, as you well know. If you don't take the right basis, like the,
Yeah, and the separable basis is wrong. We know that.
But what do you mean by wrong? I mean,
It's wrong because it doesn't give you the right physical results because the S matrix is diagonal.
No, that's another story, but you cannot say that it's not, I mean.
But yes, we know, because we know for large U1 transformations what happens. We know the S matrix of electrodynamics. Now, BMS may cloud the mind of people because it's gravity, boo-hoo, but look at gauge theory, right? There you know that the S matrix is diagonal in a continuum index.
No, but the S matrix is another story.
And
But
but if you do a dressing, right, it does exist.
But the dressing is not satisfactory, as you know. This dressing also creates an infinite tower of hard particles when you do this dressing. And precisely that's why we wanted to go back to this picture of BMS representation, precisely because to try to go away from this Fadeev-Coolidge or Kibble dressing, which also creates an infinite tower of hard particles.
Well, it creates but a finite energy tower, right? I mean, it's not that you are creating, it's just a number that diverges, but not, say, the energy of that cloud. In fact, the energy is as small as you want. Right?
Yeah, but there, you know, this ambiguity about this. Well, okay.
Well, I mean,
yeah, sure. Okay, so let's continue. So soft, yeah, okay, there is some possibilities. Just to make contact and then conclude, yeah, okay. So we have BMS particles which have support on this finite dimensional orbit. And if we do some Fourier transforms, then we can have various representations for them. And indeed, we try to make contact with Strominger phase space. So just to give very quickly the idea and then conclude. So originally, we take the supertranslation eigenstate. Just to be clear, this is not the basis that we want to use to have separable Hilbert space. It's the orbit of this, and then you take away. I mean, just to be clear. Clearly, these guys are not normalizable in the big space. So there's a whole discussion. I mean, anyway, so you have a hard and soft decomposition. So in other words, these states, you can think about them like labeled by momentum, and then the soft charge. Okay, so that's one representation. And this is the one that comes naturally from the point of view of orbits and irreducibility. But then you can say, oh, okay, but still I can do a formal Fourier transform, just like we would do to go to the position, fields in terms of positions. So then you have a function of the space of cuts, but you can again play some game. And just to finish, you see you can also think about these another basis, which would be like eigenvectors, in that case of position and Goldstone modes, which would be like this. Again, just to make contact with some other works. And you could also play some game and have mixed cases. And this one is particularly appealing, I would say. Okay, good. So, conclusion. So, although BMS representation theory has been known for since the 70s, some physical interpretation, and especially in terms of modern language and investigations, was perhaps missing. And so it's also a nice source of inspiration to do that. And that's what we did with this, in particular, hard and soft decomposition. Yes, so there is this splitting. So just to repeat, it's not linear, and this is related to the subtle supermomentum conservation. And as I just showed, there is a variety of bases that you could be interested. And now, of course, to do real physics, that's a whole other story. What is the right basis, and if things can go wrong or not? About this, I have absolutely nothing to say, and I'm totally open about that. So the goal, as I said, was to try to build a BMS invariant QFT. Of course, this is too difficult. We just took something much simpler, which was to revisit the space, the Hilbert space of states. And what we found, since we have, and I insist, separable Hilbert space of states for one particle, as long as you take the Fock space of one such particle, it's still separable. If you take a countable connection of such Fock spaces, it's still separable, but it's not clear that it's enough to do real physics, like S matrix. So then that's a big question. And indeed, the big question is, does really a BMS invariant QFT exist? That's, of course, some nice thing to go forward with this logic. And also because it would be nice if such a would-be existing BMS invariant QFT would satisfy some physical requirements like, I don't know, trying to make contact, how to recover usual Poincaré QFT, so something like a correspondence principle. And also whether such thing would keep its promises like infrared finiteness and flat holography. So thank you very much.
So can you say something more about generalizing the cluster decomposition principle?
Aha. Okay, so well, maybe, I don't know. Well, if someone else does it instead, that's good as well. No, I just mean that there is a nice notion of distance on the space of gravity vacua. So also it's related to the fact that this quotient, so which was... So super translation quotiented by translation. This is a vector space which is unitarizable. That's very beautiful. It's a unitary representation of the Lorentz group. And related to this is the fact that you have a notion of distance between gravity vacua. And so I would like, if it's true or not, the intuition that maybe when you take vacua which are far away, maybe it damps the corresponding amplitudes. And so that's how you would get closer to some Poincaré in one given vacuum. But this is vague, I don't know. But something, yeah. But here it's, I mean, you have a unique BMS invariant vacuum. Huh? This we would believe, right?
No, please. No, yeah, since this is meant to be a discussion, I had a question. So I think what we are seeing is exactly what you were describing. So BMS particles, they are, each of them independently, they form a separable Hilbert space. When you're trying to think of them as being Poincaré particles, you have infinitely many separable Hilbert space, but they look as being non-separable in the basis of Poincaré particles. So nonetheless, from the math, as BMS, in these other states, they are separable. But then, I understand you want to say that the physics is wrong, that this is what you would like to say, right? The good states, they are the Poincaré states, and therefore, as in terms of those states, these are non-separable. But then my question is, how are you thinking of, we are thinking, I guess the starting point of all this was the S matrix seems to be BMS invariance. This is what we learned from Strominger, and yet we see that the hard states, so the usual Poincaré particles, if we think of them as being BMS particles, they cannot conserve supermomenta. Something is missing. So clearly there is a need to add some other states. And these other states, and I mean, we also know this time, this is Keeble, FADF, Coolidge. There is a need to extend the Hilbert space to make sense of the S matrix. And here the question was, okay, there is a guiding line in the Hilbert space, which is representation theory. And from that perspective, we need something else. And so, yeah, perhaps the question is, how are you thinking of this? Yeah.
You can branch the BMS representation in terms of Poincaré, and then you get separable, non-separable because you have this. But when you do that, you are summing over different vacua, and you have a linear. So I haven't understood this. You have a linear superposition.
No, I think Yannick just meant it may look like non-separable. If it's separable, it's separable.
but because there is a one parameter sum of the different vacua? This is the question. I haven't understood the statement.
Maybe we should be clear about what I'm saying. So I mean, this is branching. So we start with a BMS particle representation. Then you choose a subgroup. This is what we call gravity vacua. Maybe the wording is not, what we call gravity vacua is a choice. You're an observer, you're living in around you see Poincare group, so you choose one Poincare group. And you decompose your BMS representation as a sum of Poincare representation. I mean, this is part of the work which was not, that we did, is making this very explicit for these BMS particles. And there you see that one BMS particle is made up of an infinite numbers of usual Poincare particles. But of course, it's just...
No, by definition, they're on all vacua. I mean, since it's... because all this is BMS invariant, so...
No, it's not in vacua. I mean, it's just that you're trying to read...
So, for instance, I can... Yeah, okay.
Maybe we don't understand.
So, this is my Poincare. So I take a BMS particle in this sense. The Poincare little group, let's say it's a massive particle. So it projects on a massive momentum, so it has SU2 as a little group. And let's take a case which is not a hard supermomentum, so it can have a different BMS little group, and in that case, one possibility was U1. Okay, so I assume I have my supermomentum like this. Then the branching rule is telling you have to branch the Poincare little group to the BMS little group, and this will tell you what are all the decomposition when you branch BMS to Lorentz. And that's the rule. And so in particular, imagine that you have, for the U1, you take a spin J representation. I mean, just helicity J, strictly speaking, J. Then, what would be the corresponding result? You would get all massive particles starting from, So an infinite tower of massive particles, all with the same mass, and starting with spin J. That's one of the branching rules, just to give you one example. And you can see, for instance, in this case, that everything is countable. When it's massless, it's more tricky, because there you have things that look like formal sums, but even that is a bit tricky, because it's a bit like, even in the massless case, just take square integrable functions on R2. Now pick polar coordinates, and you think about this like in terms of the, I mean, you can also, yes, so I said the R, L2, you can think about them, okay, I will distinguish between angles and radial. Well, you have all possible, so R2 is made of all possible circles of all radius, from 0 to infinity. Okay, and know the angle, I can do usual Fourier transform, okay, the Fourier decomposition. So this is separable, we know very well. We know very well this is separable. And formally, it nevertheless looks like a continuous sum. So it's a bit tricky. It depends on the basis that you choose. To be separable, it's enough to have one orthonormal basis which is separable. So of course, you have to finite norm. Yeah. So, I mean, this is similar to this. Yeah.
So you had some relation to existing literature, the last couple of slides, which went a bit fast. Maybe if you can go back.
Yeah.
In particular to the work of Strominger, where they addressed with the super translation Goldstone. So what more do you want to say here or achieve?
Oh, me? About, sorry, this point?
So you made a I think it was the previous one, or somewhere in there, you made a connection to the, so I guess Stromich had this paper, something called soft gravitational S matrix or something like that, where they address with the super translation goldstone, and I'm wondering what more do you want to do here? Like,
well, let's say, I would say that these kind of things look like, I mean, to do QFT, we know that we don't work usually in a position basis. We prefer to work in the momentum basis. It has its own problems, of course. But so here it's more trying to argue that a priori one of the nice bases is more this one than this one, or more precisely than this one. So that maybe this is not the best choice of variable to address this problem, trying to do the analog of what you would do in a usual QFT, where you don't take the... What I try to say is that usually in QFT you don't take eigen vectors of the position operator, right? You take them of the so that's what I try to say here. So I would do this. I would not use these variables, if you really ask me. I think it may be part of the reason maybe people see, I mean, it has its virtues, but maybe to address the issue of what is the proper Hilbert space, maybe it can be partly misleading. That's what seems, I mean, I don't know what my co-authors would think about that, but I would phrase it like this.
Yeah, so maybe to, let's say, try to continue on this discussion, separable, non-separable, to see if I understand, and maybe there's a, you know, a problem of traduction of two languages.
Yeah, I think so, yeah.
So the usual perspective is, let's say that it's the symmetry breaking mechanism. So, you know, so there's 2 points. First, the symmetry breaking mechanism is labeled by the memory operator, right? So that's usually what is. So what is the connection? So that's the first question. What is the connection between the memory and the memory operator is a soft operator, right? It's not something you get from the charge. So what is the connection between the memory operator is the integral of omega, you know, or omega?
At least the one in the sense of Wald and collaborators.
Yes, exactly. In the sense of,
it's the soft charge. In our language, it's the soft charge. So this d squared n. So you see, it's really one of the labels. So this is the memory.
It requires the decomposition of the momenta p. So the total mass aspect is a decomposition into soft and hard. But the hard part is a sum of your hard part. So I don't need exactly the usual decomposition soft hard is the one which is linear versus quadratic. It's not exactly the same thing as...
No, but that's why I did not use the name, but the closest thing is this soft charge.
So then the point of separability is that nobody has ever proposed a scalar product between 2 vacua which have different memories. Okay, that's the open problem in the system. So it's a linear state with memory 0 and a state with memory... What? Yeah, it should be 0.
Yeah, that should be 0. But the question of separability is if each of these vectors is finite or delta function norm.
Well, no, it's the usual problem is that they are non-separable, right? So here...
No, but again, you see... No, just to be clear. No, but then...
Do you propose, in your case, do you have a proposal?
But precisely, we propose that that's the wrong point of view, because as we are used, supermomentum states, they are not normalizable. So far, so good. No problem with that. That's not what you do. You take an orbit, and then you have, you take the square integrable function in your orbit. Although naively, one supermomentum basis state is not normalizable, nevertheless, that's not what you do. You see? So
the big question in the field is what is the scalar product of state with memory 1 with state with memory 2? So what is your answer to that?
I guess it's infinite, but that's not a problem. In the same sense, that's like saying that in usual QFT, the momentum basis is not good because I get infinity. No, 0 or infinity if you regularize as always. But I mean, our point of view is that it's as good as the momentum basis in QFT.
So take wave packet of memory 1 with wave packet of memory 2. I mean, I'm just trying to see if you have a specific...
yeah, we have a two-point function with one particle BMS state, another particle BMS state.
Yeah.
That's what we want to see.
Yeah, I want to see the
formula.
explicit formula. Could you write that? Because let's say, you know, Strominger has proposed what would be, you know, with these Goldstone modes, what could be this correlation function. So the question is whether they agree. Or
No, but this is second order. We do one particle. Me, I said I do one particle. No, but again. No, but again. Of two, I mean, again, two supermomentum states, their momentum, it's infinite because it's not even the good question. For one orbit, it's not defined. That's not the...
centered around memory 1 or whatever training states. I mean, at some point you have normalizable states in your space.
No, but I don't know how to... Yeah. Peut-être qu'il pourra...
Just a comment about the overall logic. We don't claim that we understand everything about
Yeah.
physics. So here the starting point was, if we believe that the S matrix is organized by the symmetry, maybe this is the question. To which extent do we believe that BMS symmetry is fundamental? It's fundamental, it's organizing the inlet space, and there you have to at some point go through representation theory, and this is what we want to do. And which of these representations are physical one? Whether they are useful or not, I think this is to be worked out. In particular, there, one thing, I think one of the messages that we see from representation theory is that there is more that we would have expected. For example, we are all using the word gravity vector, but I think a big part of the problem is that we are not all at the same intuition of what this is supposed to be. So, for example, one thing that you should go, whether or not it's good physics, I don't know, gravity vector states is the zero momentum representation. Yes, they are genuinely normalizable, separable, whatever you want, as good as you might want. States with zero, yeah, of course, they are all.
They are normalizable, there is continuum now, but it's not separate.
No, come on, it's because, you take this example. No, Massimo, work this example explicitly. Massimo, work this example explicitly, and you will see precisely it's not the same basis for which you have here normalizable states and normalizable states here. It's just this. Yeah, but
if you choose if at each R you define the normalizable states of R, it is R.
Yeah, no, this I...
Then
Sure.
of course you have a non-separable space. So you are doing the first choice in which R is not different than momentum or position of a particle, right? So it stays labeled by different R, right? And L2 normal.
Presumably in the same sense as here. Yeah, in some sense, yes. So yes, sure, but at least if your starting point is okay, me, I'm happy. I mean, you cannot tell me it's not, you see what I mean. At least there is a meaning in which there is a Hilbert space which is separable at the very beginning, for instance, a normalizable state. Then when you try to make contact with Poincaré, there may be tricky things and tricky changes of basis.
The problem is that for each R, so R defines a super selection set, right? In which the S matrix, I mean, the evolution is always in the same R. Now, if you want to recover the usual axioms of field theory that says that, oh, there is one normalizable vacuum, then you should make the norm of the eigenstate R equal to 1. It cannot be equal to 1 because so
Yeah.
it's just a contradiction between these two languages.
But it's,
Yeah, but
It
on
just-
the other hand,
well,
so
okay.
here the starting point is the invariance of the S matrix, no? That we can debate or not, no? In your perspective, it's not, no? Because if you change, if you you move from one super selection sector to another, so you covariant. Yeah, so it's different perspectives, so not.
There's a very important claim that you have a scalar product. And it's very important, and that's what I'm asking. So I just want to see, let's say for the vacuum sector, P nu is equal to 0, exactly. So what is the proposed formula, even if it's a formal path integral? I just want to see, what is your formula for the scalar
But seriously, just wave functions,
phi of P.
square integrable wave functions on your orbit. So it choose a memory, act with the Lorentz group, and for each of them, it has weight 1, and you write the integral. So I cannot say more. I mean,
No, do you have a function wave?
no, but I can write L2 if you want. But R measure, yeah, if you want, but of course. Yeah.
Okay, so then...
The physics is hard, this of course. So for instance, in this case, for this kind of branching in the massive case, you can use, yes, the Plancherel. You use Peter-Weil theorem. But that's why massive behaves slightly nicer than massless. And then you use Peter-Weil theorem since it's a compact group. No. Here in the generic case, they all so all spins appear generically.
Because usually in the Lorentz case, only principal series and discrete series appear.
No, but here it's the Plancherel of the of SU2 of this one. Yeah.
Okay, so maybe it's nice discussion, but there were also other questions. No, you still have a question? Yeah, exactly. So just to open maybe other.
No, but it should be fast. It's very, very naive. So, I mean, whatever vacuum you choose in the sense of Ashtekar or whatever cut you choose, the associated Lorentz group will not commute with supertranslations. So I just wanted to understand, why are you asking for an SL2C invariant injection of the supermomentum? And could you conceive a construction in which is not SL2C invariant, and on the other hand it is linear? Is this something that can you...
A priori, since the wave function is for all cuts, you would not like a choice of cut, right? I'm not sure that was your question, but...
But why are you asking it to be Lorentz invariant? This is what is not clear to me, because when I think of supermomentum, I think about something that doesn't commute with the Lorentz subgroup.
But one of them, right? But you want an orbit? I mean, one supermomentum.
Yes, will not commute with...
Yeah, but we want all of them, or we want an orbit, no? Or... Yeah, I don't understand. Yeah.
Also, in another direction, I would like to know if you will agree or not with the fact that if we don't have soft momenta, the quantum field theory of BMS particle, or a quantum field theory, BMS quantum field theory, will be a decoration of a Poincaré field theory.
If you have just soft...
Only hard momenta.
Only hard momenta. Oh, yeah, sure. Okay. No, that's the that's the problem, and that's why. Okay. It depends what you mean, but at least this is what we wanted to insist. Where was it? That the sum, it's not possible. You cannot do it because it would be nice. Let's imagine we would just have BMS symmetry, because there is the surprising thing that is as follows. If you take any hard representation of, if you take any representation of Poincaré, I can lift it and see it as a representation of BMS. That is for free. That's a fact. And basically, this is the hard representations. So this is okay. But now, if you try to make UFT out of these, which keeping supertranslation symmetry, then you will run into problems because although you will preserve momentum, you will not preserve the supermomenta. You will produce soft parts. You cannot have a BMS invariant theory, QFT, if you want, of only hard particle. It's not possible.
Okay.
Yeah. So that we are forced to do that. Or we are forced to leave BMS. I mean, I don't know, huh? I have no prejudice. But at least you cannot just do usual one and having BMS in mind. Yeah.
Okay, so I don't see further questions, so we know that there are things to discuss over lunch, but then I propose to thank Xavier again, and maybe move towards lunch.